Hello, and welcome everyone to the impromptu session, to the last session of this conference. We'll start with John Langford. If you want to use this one.
Okay, so this is about empirical likelihood for contextual bandits. There's a paper in Archive about this, which if you go and search for it, you'll find it. So who knows empirical likelihood here? A few people. So partly I'm telling you that this is a hammer that I found to be really actually pretty useful. And so maybe you want to look at it yourself. John Ducci, I think, has also been playing around with empirical likelihood. So I'll just go through what we were able to do with this, and maybe you'll see why it's so useful. All right, so when you're doing contextual bandits, you want to try to get a value for a policy. The value estimates for policies typically break down to some form where, let's see if I can, yes, okay. So you have some importance weights related to the policy you're trying to evaluate. You have some rewards that you observed, and it's kind of the empirical expectation or the true expectation of these importance weights times the reward when you're trying to do counterfactual evaluation. So let me give that in a little bit more detail. You have some behavior policy, which generates your data. That behavior policy has some probability of choosing each action. When you're trying to evaluate a new policy, there's some ratio between the probability that your new policy chooses that action and the probability that the behavior policy chose that action when it was recording the data. And now you want to importance weight in order to get an unbiased counterfactual estimate. Okay, so that's straightforward. That's kind of basic technology that we've used for a long time. And now the question is, so if you have some data set, if you knew what the proportions of W and R were perfectly, you could do a perfect estimate with zero error for a policy. But you don't know that in general, because all that you have is a sample from whatever distribution is generating your W's and R's. And so you need to somehow fix things, right? So obviously you can just straight up use these importance weights. That's the IPS estimator. But maybe something better that you can do. All right, so we can imagine that there's some unknown ratio or fraction of WR pairs. And then we can try to discover that using empirical likelihood. So in empirical likelihood, what happens is you say, I want to maximize the likelihood of Q given the data that I have and some normalization constraints. So I'm going to normalize this Q so that the distribution of the factual distribution and the counterfactual distribution both normalize to 1. So I don't want to go into details about that, but you add some constraints. Then you have a constrained optimization of a log of Q. All right, so then you can kind of have an intermission where you play around with duality, and you discover it's actually pretty easy to compute this constraint. You can essentially do it in linear time. And then you can apply this to confidence interval calculations. So if you're trying to do confidence intervals for contextual bandits, there's kind of two obvious things you can start with. One of them is you can say, look, everything is asymptotically a Gaussian. And so I'm going to pretend that I have a Gaussian with some empirical variance and use that to define my confidence interval according to it being a Gaussian. And what this typically does is it gives you a pretty tight confidence interval that's a little bit weird because it undercovers, right? And the critical value here, by the way, is the number of samples divided by the largest importance weight in your data. Right, so another thing that you can do is you can say, oh, look, everything is really a binomial because I'm going to randomly round my weights to be either the largest weight or 0. And then you get a very conservative confidence interval, which never undercovers. So, okay, so that seems nice. And then you can do the empirical likelihood, and you get out a pretty tight confidence interval, which never undercovers empirically and which is asymptotically correct. So this gives us a much tighter confidence interval, which is very similar to the Gaussian, but it's actually accurate. So you can actually rely upon it in a way which you can't for the Gaussian. So this is on some synthetic data source. We also did this on real data. We got like a factor of 3 improvement. And then, of course, we were like, oh, well, okay, so this also gives us an estimator. It's a new way to get estimators where you impose these normalization constraints. It seems like the estimators are actually quite good. And then you can also get better update rules because you can try to optimize the confidence interval lower bound. I'm at 0. And yeah, it seems to work well. All right, thank you. Any questions? Okay, so in archive if you want to see.